So now that we've been exposed to the concept of what a sequence and what a series are, we can talk about classifications of different ones. And so one particular classification of a sequence or a series is called a geometric sequence or a geometric series. And by definition, a geometric sequence is one for which each successive term is found by multiplying the previous term by some sort of a common ratio. Right, so a very simple example of a geometric sequence would be a sequence that starts with 10 for its first term, and then its next term might be 5. Which leads us to the idea that what was multiplied there was a common ratio of 1/2. Right? So the next term would be 5 times 1/2, which means 5 halves. The next term would be 5 halves times 1/2, which would be 5 fourths. The next term would be 5 eighths. The next term would be 5 sixteenths, and so on. This is an example of a geometric sequence for which the common ratio, which is usually called r, the common ratio is 1/2. Right? So if you ever see a sequence that's like this, that has a common ratio, that has something in common that's being multiplied to the previous term to get the successive term, it's a geometric sequence. I did have a mistake here, so I've got that corrected here. But there is a test, we've been talking about these tests for convergence, a test called the geometric series test. And it's actually very simple. An infinite geometric series converges if and only if the absolute value of the common ratio is less than 1. Okay. So even to say that in other words, that means the common ratio has to be between -1 and +1, right? Not including 1 or -1. Furthermore, and this is important, if that absolute value of the common ratio is less than 1, if it does converge, then we can actually say what the series converges to. We can say that the sum of the infinite geometric series will be this, right? So, that example I had on the previous page where I was saying we actually started with 10, I believe. We did 10 plus 5 plus 5 halves plus 5 fourths, and so on. This was an infinite geometric series whose first term was 10 and whose common ratio was 1/2. So according to this formula up here, well, first of all, by the geometric series test, this does converge. It will equal something because my common ratio is less than 1. Right? But we can actually find out what it is equal to by using this formula. The infinite sum will be 10 over 1 minus 1/2. That's 10 over 1/2, which is 20. Okay? So this is the geometric series test. Right? If the absolute value of the common ratio is less than 1, it converges. If it converges, we can even say what it converges to. So another just example for you. For the following series, find the first term and the common ratio, and then determine if the series converges or diverges, and if it converges, find the infinite sum. This should be something you guys can pause the video and do for yourselves, so please do that now. So you should have found that your first term was 9, and your common ratio, and the common ratio is what I need to multiply to sort of get to the next term. Often an easy way to do that is to look at like -6 divided by 9. Or 4 divided by -6. Either one of those things is the ratio of the terms, the ratio of this term to this term, this term to this term. Turns out both of these ratios simplify to being -2/3, right? So we have the sense that because this is less than 1, because the absolute value of that is less than 1, it means that this will converge. And we want to say it converges by the geometric series test. Okay? So now, if it converges, find the infinite sum. So this is where we would say, okay, the sum will be 9 over 1 minus -2/3. That's 9 over 5/3. And so if we multiply top and bottom by the reciprocal of the denominator, we'll end up with 27/5. And so that is our infinite sum. Right, this entire thing, if we were to add it up to infinity, would get me to 27/5. One more example for you. For the following series, find the first term in the common ratio, then determine if the series converges or diverges, and the same thing, if it converges, find the infinite sum. So work that one out. We'll do this one more quickly. Your first term is 5. Your common ratio here is, well, if we look at sort of what's happening here, to get from this term to this term, I would need to multiply by -3 halves. And if you didn't see that, and that's a really ugly 3. If you didn't see that immediately, remember the other way that you can find these things is by looking at -15/2 over 5. Or picking other ones, doing 45/4 over -15/2. for both of these fractions, if we simplify them, they both lead us to the common ratio of -3/2. But in this case, our conclusion is that this series does not converge. In fact, this diverges because my common ratio, the absolute value of that, is not less than 1. And for all these problems where we talk about convergence and divergence, I want us to be writing a sentence about why it converges, why it diverges, about what the statement is, right? So in this case, because the absolute value of the common ratio is greater than 1, I just realized I missed an I there, is greater than 1, the infinite series diverges by the geometric series test. And note, when I write these sentences, I want a reference to the name of a test. But in this chapter, we're going to have like 10 tests. I want to know what the name of the test is each time.